Hey kids, welcome to section 2.1, organizing data. Today we're going to learn how to organize data using a frequency distribution. So suppose a researcher wished to do a study on the ages of the 50 wealthiest people in the world. The researcher first would have to get the data on the ages of the people. In this case, these ages are listed in Forbes magazine. So over here are the ages. When the data are in original form, they are called raw data and are listed at the right. So here's all the ages of the 50 wealthiest people in the world. Since little information can be obtained from looking at raw data, the researcher organizes that data into what is called a frequency distribution. And here's the definition right here. Frequency distribution is the organization of raw data in table form using classes and frequencies. So each raw data value from the group of 50 is placed into a quantitative or qualitative category called a class. And the frequency of a class then is the number of data values contained in a specific class. So here's a frequency distribution for the preceding data set. We have class limits here on the left. This is the different groups that we're putting the data into. Then the middle column is the tally column. So every time I have a number in between those two numbers, I put a little mark. And then I add all my tallies up to get my frequency. Notice that this number down here at the bottom for total values should be the same as the number of values you started with. If it's not, then you missed one somewhere. Okay, so the categorical frequency distribution is used for data that can be placed in specific categories such as nominal or ordinal level data. So here's an example of us making a frequency distribution. 25 Army inductees were given a blood test to determine their blood type. The data set is listed below. Construct a frequency distribution for the data. Well, we're going to have a couple different columns in our table. First, we're going to have class. Then we're going to have tally. And then we're going to have frequency. And so in the class, we're going to list the different blood types. So it doesn't matter what order you list them in. A, O, B. I just went down the list and found different ones. There are 4 different ones. And then what we're going to do is we're going to go through the table of values, the raw data, and we're going to tally up how many there are of each. Now, there's a couple different strategies. You could just count how many there are and put them there. You can just go one by one by one and add them. I'm just going to go one by one. So we got 1 for A, 1 for B, or 0, or sorry, 1 for B, another for A. So I'm just going to go through and I'm going to put tally marks. Again, it doesn't matter if you do the tally marks as you go, one by one, or if you wanted to say count how many A's there were and count how many B's there were. That's also totally a good strategy. Okay, so I'm just going through B, O, A, B, and A. Okay, so when I was finished, I had 5 A's and 9 O's and 7 B's and 4 AB's. Make sure that, it's a nice quick check. Make sure that these numbers in the frequency column total the amount of data values you had to begin with. And so I got 14 and 11, that's 25. So we're good to go. So that's called a frequency distribution. And there's ordinal or nominal level categories, and you can put them into their own separate classes, tally up how many there are of each, and then state the frequency. When the range of the data is large, however, the data must be grouped into classes that are more than 1 unit in width in what is called a grouped frequency distribution. So if we look at this table here for the 50 ages of the wealthiest people in the world, notice that they are not single numbers over here in the far left column, but they are spans of numbers. And so this is called a grouped frequency distribution. This table actually goes with a totally different 50 value. A distribution of the blood glucose levels in milligrams per deciliter for 50 randomly selected college students. So they collected data and they put it into here. Okay, so the values of 58 and 64 of the first class are called the class limits. So here's the 58 and here's the 64. The lower class limit is 58. It represents the smallest data value that can be included in the class. So all of your lower limits are going to be on the left-hand side. The upper class limit is 64. It represents the largest data value that can be included in the class. So these are all of your upper limits. The numbers in the second column are called the class boundaries. These numbers are used to separate the classes so that there are no gaps in the frequency distribution. The gaps are due to the limits. For example, there's a gap between 64 and 65. So right here, after 64 and before you get to 65, what if you have a decimal? Where are you going to put it? So that's why class boundaries were introduced, so that you can notice that one class boundary backs right up against to the next class boundary. The class width for a class in a frequency distribution is found by subtracting the lower or the upper class limit boundary of one class from the lower or upper class limit boundary of the next class. So for instance, if I take 58 and subtract 65, or vice versa, I get 7. Or if I do 79 and 86 subtracted, I get 7. I could also take 71 and 78 and subtract them and get 7, or 92 and 99. So that's called the class width. It's how wide the classes are, not how wide each class is. So the basic rule of thumb is that the class limit should have the same decimal place value as the data, but the class boundary should have one additional place value and end in a 5. So for instance, my data were all whole numbers, so my class boundaries are going to have one decimal or tenths. So this page gives you a recipe, if you will, of how to construct a grouped frequency distribution table. There are 6 things to remember. There should be between 5 and 20 classes. It's preferable but not absolutely necessary that the class width be an odd number. The classes must be mutually exclusive. That means they can't overlap. The classes must be continuous. That means there are no gaps. The classes must be exhaustive. That means every value in the raw data can be found somewhere in the frequency distribution. And the classes must be equal in width. So we don't want to have one class width and then somewhere else we accidentally have a different class width. They should be consistent. Okay, and then this procedure table you can look back on if you need to remember the steps. Going over them now is probably going to confuse you because you have no idea what I'm talking about. So you can look back at that blue table and that can help you remember how to do it. Okay, so here's our first example. These data represent the record high temperatures in degrees Fahrenheit for each of the 50 states. Construct a grouped frequency distribution for the data using 7 classes. Okay, so here are the data for the high temperatures in each of the 50 states. We need to construct a distribution. Well, we need some info first. First, I need to figure out what the maximum value is, what the minimum value is, what the range is, and what the class width is. So the maximum value in the table is going to be 134, and the minimum value in the table is going to be 100. Yes. So maximum value is 134, minimum value is 100. That makes the range be 134 minus 100, which is 34. And the class width, we take the range, and we divide by the number of classes. It does tell us that we're using 7 classes. Now, this is going to give us a decimal of 4.9, but we can't, it's kind of hard to have a class width that's a decimal. So we're going to always round up, and so we're going to get 5 as our class width. All right, so now we can set up our distribution. So we are going to have 4 columns: class limits, class boundaries. All right, class boundaries. Then we have tally, and then we have frequency. Okay, let's go down a tiny bit. All right, so we're going to make this big old table. All right, so the first thing we're going to do is write down your minimum value, and then we're going to put a dash. Then we're going to take the class width, which is 5, and we're going to add 5 to it to get the next lower bound, 105. And I've got 7 classes, so we're going to do this 5 more times. So 110, 115, 120, 125, and 130. Then to find the upper limits, we're going to take and subtract 1 away from the next lower limit to get the previous upper limit. So 104 minus 1's, or 105 minus 1 is 104. And then I can either look at 110 and subtract it to get 109, look at 115, subtract to get 114, or I can keep adding the class width to get to each of the next upper limits. So I can say 119, add 5 is 124, add 5 is 129, add 5 is 134. Now the class boundaries are going to be that 0.5 number that's going to close the gap between the classes. So I'm going to go from 99.5 to 104.5. And then my next one's going to start at 104.5 and it's going to go to 109.5. So notice now I have no gaps in between the classes. So 109.5 to 114.5, 114.5 to 119.5, 119.5 to 124.5, 124.5 to 129.5, 129.5 to 134.5. Then I'm going to go through and I'm going to tally them all up. So I'm going to do 112 is going to be here, and 110 is going to be here. Okay, so we're going to go through and find them all. I'll just go ahead, and it's going to take forever to do it, so I don't want to waste a ton of time doing it. 1, 2, 3, and 13. 7. All right, so our frequencies were 2, 8, 18, 13, 7, 1, and 1. So this is a grouped frequency distribution for the data. Class limits, class boundaries, tally, and frequency. Again, this total frequency over here should equal 50. So we've got 10, we've got 28, 29, 30, 43, 50. So we're good to go. All right, so sometimes it's necessary to use a cumulative frequency distribution. A cumulative frequency distribution is a distribution that shows the number of data values less than or equal to a specific data value, usually an upper boundary. So notice that the values here, this is a cumulative frequency distribution. Notice that all of the numbers here match up with the lower limits, or lower class boundaries. Notice also that it says less than. That's because we're continuously adding all of the values in the table that are less than each of the different boundaries. Cumulative frequencies are used to show how many data values are accumulated up to and including a specific class. And after the raw data have been organized into a frequency distribution, it can then be analyzed by looking for peaks and extreme values, The peaks show which class or classes have the most data values compared to other classes. And these extreme values, called outliers, can show large or small data values that are relative to other data values. So you can see where the different values are found. You can see where the most, which class most of the values are found in, so that you can then compare to see where the greatest is, the least, and look for any trends. When the range of the data values is relatively small, not like the last one, a frequency distribution can be constructed using single data values for each class. This type of distribution is called an ungrouped frequency distribution. So for instance, we have this data here, miles per gallon for SUVs. The data shown here represent the number of miles per gallon that 30 selected four-wheel drive sport utility vehicles obtained in city driving. Construct a frequency distribution and analyze the distribution. Okay, so if we look here, we have 30 different values to represent miles per gallon. We need to do an ungrouped frequency distribution. That means every value is going to be listed. We should still, so we don't have to do a maximum, minimum, range, class width, because we're not putting them into classes. So we need to look at class limits. We need to look at class boundaries. Then we have tally. And then we have frequency. So if we're looking at class limits in an ungrouped frequency distribution, we're going to just list every different value that we see. The smallest value is a 12, and the biggest value is a 19. So 12, 13, 14, 15, 16, 17, 18, and 19. Now notice there's not an upper limit and a lower limit. It's just the limit. We can do class boundaries to close the gaps between the different classes. So we can subtract 0.5 and say the first one is from 11.5 to 12.5, 12.5 to 13.5, 13.5 to 14.5, 14.5 to 15.5, 15.5 to 16.5, 16.5 to 17.5, 17.5 to 18.5, and 18.5 to 19.5. Then I can go through and do my tally. So again, I could either count. This time, I don't know, we'll count and see how many there are of each. So there's 1, 12, 2, 3, 4, 5, 6. Looks like 6 12s. And then 13s, we got 1 13. 14, 1, 2, 3. 15, 1, 2, 3, 4, 5, 6. 16, 1, 2, 3, 4, 5, 6, 7, 8. 17, 1, 2. 18, 1, 2, 3. And 119. So there is a frequency distribution that's ungrouped. It does say to analyze the distribution. And when you analyze the distribution, you want to show me or tell me about any increases, decreases, any peaks in the data, things like that. So one thing that you can see is that between 15 and 16, that's 14 numbers. That's almost half of the data values falling in that one or those two classes. So one thing we could say is almost half of all values were 15 miles per gallon or 16 miles per gallon. There are other things that you can say. You can say 16 miles per gallon was the most popular, and 13 and 19 miles per gallon were the least popular. So those are also things you can say. The different types of frequency distributions shown in this section are the following. There were three. One was the first type is used when data are categorical or nominal, such as blood type or politic affiliation. This type is called a categorical frequency distribution. So that was the first one we did. The second type of distribution is used when the range is large and classes several units in width are needed. This type is called the grouped frequency distribution. That was the second one we did. And then another type of distribution is used for numerical data and when the range of data is small. Since each class is only one unit, the distribution is called an ungrouped frequency distribution, and that was the last one that we did. So all the different types of distributions are used in statistics and are helpful when one is organizing and presenting data. And there's lots of different reasons for why someone would construct a frequency distribution. Number one, to organize the data in a meaningful and intelligible way. Number two, to enable the reader to determine the nature or shape of the distribution. Number three, to facilitate computational procedures for measures of average and spread. Four, to enable the researcher to draw charts and graphs for the presentation of data. And number five, to enable the reader to make comparisons among different data sets. So these would all be valid reasons as to why someone would want to make a frequency distribution. All right, let's do our application problem, ages of presidents at inauguration. So the data at the right represent the ages of our presidents at the time they were first inaugurated. Number one, were the data obtained from a population or a sample? Well, if you think about it, we've only had 46 presidents. At the time this book was written, there had only been 44 presidents. So all of the data were obtained from a population. A population of all presidents at the time this problem was written. At the time the problem was written. Okay, number two, what was the age of the oldest president? If you look in the picture, looks like the oldest president was 69. The oldest president was 69. Number three, what was the age of the youngest president? All right, so the youngest president is 42. The youngest president was 42. All right, and then this slide asks us to construct a frequency distribution for the data. Use your own judgment as to the number of classes and class size. So let's see, we need to find what the maximum value is. We need to find the minimum value. We need to find the range. And then we have to find the width. So the maximum value in the table is 69 we just found, and the minimum value in the table was 42. So that gives us a range of 27. And if you have, let's say we have 7 classes. That sounds like a good amount. Then 27 divided by 7 is going to be 3.9-ish, but we're going to round that up to a class width of 4. So let's see if we do class limits, and then we do boundaries. If we do tally And if we do frequency, okay, so our smallest number is 42, so we can start with that as our first class lower limit. And then we take the width, which is 4, and we go up 4, so that's 46, and that's 50, 54, 58, 62, 1, 2, 3, 4, 5, 6, I need one more, 66. So I should have 7 classes, class width of 4. Then to find the upper limits, you can look at the next lower and subtract 1. So that goes to 45 and 49. Now you can keep adding 4, or you can go to the next lower to find the previous upper. So this would be 53 and 57, 61, 65, and 69. Then your boundaries are going to be a 0.5 step in either direction. So 41.5 to 45.5, 45.5 to 45.5. Oh, no, to 49.5. 49.5 to 53.5, 53.5 to 57.5, 57.5 to 61.5, 61.5 to 65.5, and 65.5 to 69.5. Okay, so now I've got my boundaries. I'll do the frequency for you. First one is 2, then 7, then 8, 16, 5, 4, and 2. Now, depending on how many classes you chose, your frequencies are going to look different. If you chose 5 classes versus 9 classes, your tally frequencies are going to be different. Are there any peaks in the distribution? Well, yeah, it looks like there's a peak here at this 16. So we can say, yes, there is a peak at the 54 to 57 class. Identify any possible outliers. It doesn't look like there's like a couple 0 classes and then a 1. There doesn't appear to be anything by itself far away. So we can say, as presented, there are no outliers, because there certainly could be outliers depending on how you chose to do your frequency distribution. So if you had chosen 9 classes, you might have seen an outlier, versus someone who did 5 classes might not see it. Okay, finally, number 7, write a brief summary of the nature of the data as shown in the frequency distribution. So based on your frequency distribution, tell me about it. Well, it looks like the graph here is unimodal. There's one peak. So we can say the data appear to be unimodal. It also looks like it's fairly symmetric. It takes 1, 2, 3, 4 to get up, and then 4, 3, 2, 1 to get down. So we can say fairly symmetric. And then you can say maybe something about where like the middle is. We can say, and centering on, well, I guess in between 54 and 56 is kind of like 55 and a half. So we'll just say 55 years old. All right. Well, that is section 2.1. If you have any questions, please let me know. And as always, keep calm and keep trucking.